Hello, I'd like to welcome you to this presentation. My name is Baikauskas. I am a process engineer, and together with my coworker, Federico Parkkulainen, we would like to share this experience with you. Today, we will talk about a real project case we developed for a revamp of a catalytic naphtha reforming unit in an oil refinery. In this case, we will show how a simple column fractionation bottleneck that was not properly solved in the initial stage of the engineering could have had a serious impact on plant downtime and project costs, and even compromise the completion of the work. First, let's see something about the project context. The refiner's primary goals for this unit expansion project were quite ambitious. In addition to achieving a better quality of the reformate with a higher octane number, a higher plant capacity was required at the same time. What's more, improvements in the purities of the products were also expected. Secondly, for the project development, the refiner proposed a classic organization scheme in which the licensor, the specialist dealing with the reactor technology, would solve the typical basic design package. Then, a local contractor would complete the development of the standard equipment engineering following the previous guidelines. And finally, a third contractor would carry out the construction. We began our work here, and then we tried to follow our customer's plan with the intention of validating the solutions proposed in the first stage, and then be able to develop them in detail. However, we soon discovered a change was worth to be introduced. Now, I'd like to focus briefly on the process of the existing facilities of the fractionation area and the new conditions that were required. Increasing the reformate flow rate in the product fractionation zone required processing a higher load in the three columns, but especially in the first two. There was also a new, more stringent specification of contaminants for the final products obtained in the final splitter column. So, in order to get that, it was required to achieve a more demanding fractionation, that is to say, to get a better purity of the distillate in the second column, the debutanizer. This combination of requirements was particularly challenging for the debutanizer column, and at first glance, the upper section of the column needed more separation stages and a bigger diameter. As usual, on the plant side, there was no available space for another column, so the BDP's proposal to carry out the debottlenecking of this area consisted of adding a new section of 12 actual trays in the upper section of the existing column, with the aim of improving its power of separation. In addition, in order to be able to condense the top product with cooling tower water and at the same time solve the problem of column flooding due to the higher internal flows, a new operating pressure that slightly exceeded the original mechanical design pressure was proposed. This initial proposal that the refiner had in mind was technically good and even logical from the theoretical point of view, but it implied a major modification of the column, adding a new section with 12 trays, about 7 meters in height, to be located on top of the existing column. Analyzing this proposal, we found that the existing column had already been revamped in a previous project, and 7 trays had already been added in the upper section. So its height was in fact already 25% higher than the original column design height. Thus, this modification involved carrying out a work that at a height of 30 meters above the ground floor. In addition to the complexity and risk of this work, a check of the concrete foundation due to the additional weight was required. Also, a mechanical rating of the existing column was pending due to the extra weight added and due to the effect of the wind on the new total height. Of course, the mechanical re-rate of the column and associated equipment at an internal pressure 18% higher than the original design pressure was also required to be successful and hopefully not require further modifications. At this point, we decided that the revamp strategy had too many weak points and a new approach was needed. From many years of revamp experience, we knew that revamp solutions must be evaluated and solved in an integral way at early stages so that risk is reduced as the project moves towards basic and detailed engineering.
Well, we shared these issues that we highlighted before and decided with the client to take some weeks at the beginning of the project to search an alternative solution which could reduce the risks involved. We restudied the system and agreed that the main capacity limitation was the upper section of the column due to the relatively small diameter. That made it impossible to increase top reflux to get a higher purity in the top product. However, we also saw idle capacity in the lower section of the column. We could manage the increase of the flow rate there, so we focused on how to improve the fractionation power by using this idle capacity. Why not subcooling the feed? By doing this, not only did we increase the internal reflux, but also we reduced the amount of heavier components that used to reach the top of the column due to flushing. To get higher reflux rate in this section and not oversize the new reboiler, only a fraction of the feed is subcooled and fed to the original inlet connection, let's say a 15%. And the rest was fed to a lower tray in a new connection. So with these two main ideas, we got higher capacity and better fractionation with minor changes. Here, we see how the solution was implemented. With a ratio controller, a fixed percentage of the field is subcooled in an air cooler, and column inlet temperature was controlled with a bypass to avoid perturbances due to the changes in air temperature. It's worth mentioning that the required subcooling duty for this portion of the feed was managed by redesigning an existing air cooler and converting the bay in a multi-service bay. With this approach, we solve another challenge in revamping projects: layout. Existing units, especially in refineries, can be extremely cramped with equipment and pipes, and plot plan space is often scarce. As conclusions of this example we are sharing, we may say that by introducing minor modifications, we achieved a 20% increase in capacity and the required product specifications, and since the operating pressure and column height remain untouched, the solution was not subject to major mechanical or civil validations. So we could, in fact, reduce the potential risks we were concerned about with the initial solution. What can we say in general about revampings? Well, CAD solutions are not always the best option. I am not saying they aren't a good option. Most of the times they are. What I mean is, think if it is suitable for you. Most of us are a little professionally biased based on our experience. If you ask a trace supplier, for instance, how to increase the capacity of a column, they might be more inclined to search in their toolbox and offer some internal replacement that may solve your problem. In the same manner, we, as process engineers, are used to designing processes, and it comes out naturally to consider the process itself as an extra degree of freedom when finding a solution to a problem. This approach expands the possibilities. This is what we mean by saying thinking outside the box in revamping projects. Know your process and know your equipment. Only with a deep understanding of unit operations and equipment rating will you be able to exploit hidden capacity margins or rearrangements that could be used to meet your needs. In that sense, you may be able to find small process changes that can lead to cost-effective solutions. With this example, we reconfigured the lower section of the column just by incorporating a new connection and increase both capacity and fractionation power. Assure project construction viability. It must always be a priority at all stages of the project, but mainly in the initial ones. That's why it is vital to devote time in an early stage to finding rock-solid solutions. Take advantage of that stage and analyze different possibilities. Of course, keep the number of interventions on the existing facilities as low as possible. And by doing that, you will reduce impact on construction too. All these recommendations, to say a few, contribute to get a higher predictability and lower risks in the project, which are key to assure smooth execution phase. Well, that was all. Many thanks for your time. We will be available for a session of Q&A if you're interested. Thank you very much.